Hello, fellow programmers. Once again, Rodrigo Diaz here. Welcome to this Animator PLC course. And today we have a very important topic that we're going to analyze because ultimately and finally we're going to look at a laddered diagram, its components, equivalencies with their electric symbols, and the ladder diagram components. Okay, so if we're ready, let's move along. The importance of ladder diagram language. First off, why is it called like this? Its language says that we're going to start adding uh, lines or segments or ladders. As we're adding these ladders, it's going to start turning into as it seems, it looks like a ladder. Okay, something very simple, very obvious, but true. The laddered diagram language is read from left to right, top to bottom. So that's the first rule. Why is it so important? In our Animator PLC, or the software that we developed to be used in general with all these brands, is solely based on ladder diagram. The rest of these brands, let's say Siemens, for example, are also based on a ladder diagram. So yes, each brand has their own programming language. They can have structured text, sequence lettering, or block diagram, which is very used in PLC brands. But the reality is that 90% of all programmers specifically know in automation industry and such, they know how to program in ladder language. Even the operators, they know ladder diagram, ladder language. It's a language that is not very complex, but also we need to have our established basis. Alan Bradley also uses ladder diagram, ladder language. Schneider Electric also has ladder diagram. Now, I had previously said that it's very important to identify the inputs and outputs. Now, all of this that we have for contacts are our inputs. We have regularly open contacts like this. We have normally closed contacts. And what do we have here in Siemens? Normally open contacts, which they don't do anymore, but same basis. Regularly closed, regularly open, open, open. And what do we have here? A timer, which we as PLC Animator use. Alan Bradley also uses a timer like timer on delay. A TOD, TON, sorry. Same thing here, TON. So there are instructions for programming within our ladder diagram, which are used and have the same function for all brands. We have normally open contacts, a parallel, an enclaving, normally closed contacts, and we use everything all the same. Timers, coils, and now if we go to our outputs, which is everything on the right side, which I'm going to explain to you, all of these are coils. So, okay, this coil is regular, is normal. This one is enclaved. And there's another one, which, let's say this is like a latch. And this is an unlatch for Allen Bradley. But ultimately, they have the same goal and same function. Here we also see what is latch and unlatch, which are enclaving coils, which we're going to check further down. So if you know them, you know that it makes complete sense. Now, this is a normally open contact. It has a flank. We also use this. And we have a parallel, which is perfect. We also have set or latch and unlatch. We have our coils. And of course, they're all lines or segments. Now, what do they have in common? What do these brands have in common? That they use ladder diagram. So to make things easier, they use mathematical equations. We have certain uses that are programmed, but ultimately our basis is right here. Now, I know programmers that are very good at programming, and yet they don't know how to program structured text. Or every so often, this is not obligatory, but you don't need to know all programming languages. As you start growing professionally, you have certain options. And as you start requiring them for the job, because when I learned structured text, I was very young and I remember that I was working with a machine. And within our PLC, we had structured text. So I had to learn that programming language. But ultimately, I had no idea from before. I started learning as I was moving along. So when I started analyzing how they worked or how they activated our outputs and how variables changed, it made things much easier. But it's not like I had to pressure myself about regarding programming languages, thinking that I wasn't going to know how to work out on the real world. So if you know ladder language, you can work on whatever you wish without having to know programming language. So if you know how to adapt with a ladder process, you can control with anything you wish. Now another example is we have here the instructions for programming. Now remember that we order our PLC what to do through programming. These instructions, for example, they're for ladder diagram, and let's analyze them. We have regular operations or favorites, which are lines, parallels, regularly open contacts, regularly closed, latch, unlatch, etc. All the common ones. Siemens has them in ladder diagram, and they're right here. Now in general also, because this is also a combination, but we have them. Now, Allen Bradley, parallel, which is another function that is also parallel, but this one is regularly closed. This one is our coil, which is an output for activation. Our very famous latch, unlatch, all of this, we have all of this. Denied coil. There's certain things that also Allen Bradley doesn't have, like the coils, but ultimately, this is not an impossibility for us to continue programming. Because when we have them already developed, we can do the same thing, but with a different instruction. Okay? So there's certain instructions that are not obligatory. They're not an obligation to know. And in general, with the general ones, we can do wonders. Okay, so we have them. In Schneider, the ladder elements, which are more common, we have our network segment, the contact, the denied contact, the parallel contact. And for example, here we have a different instruction for Schneider, which is a parallel that has a denied contact. Is this the same for all brands? Not Allen Bradley, not Schneider, but we have other instructions with which we can run exactly the same thing. But the most basic thing, we all have it as far as ladder diagram, which is the coil, the regular coil to activate an output, our set coil, latch, reset coil, unlatch, timer on delay, which is our TON, our ton, which we had seen for Allen Bradley and Siemens. And Schneider also has this, which is timer of delay. We also have our counter up. And here we can't see this, but we have counter down. So all of these instructions, we have them in common. That's why it's so important, our ladder diagram. If we focus on this language for programming, on this programming language, and we know our basis very well, and our Animator PLC course is a very good basis for you to understand everything for PLC, and you understand exactly how to solve problems. When we move on to a different brand and they tell you, hey, we need Siemens, we can take a course, but we're not going to start from scratch because we already know how inputs are going to work. Same thing is going to happen with industrial automation. What are their inputs, their outputs? And all you need to analyze is configurations, brand configurations, their directive, which are very simple, especially for physical and virtual memories, which we're going to see. And that's basically it. How do we connect to our PLC? What type of communication do we need? How to use our software? But problem solving, which is what we're getting paid for, how to solve efficiently a problem and effectively also, we're already going to know how to solve this without needing to say, oh, well, first I'm going to take this one and then that one and then no. Now, since we know that demand for automation is huge, and also there's a lot of competition, that's where that's where we get worried. And then they're also based on other brands. So that's why it's very important. Now, moving on to our next topic, which are ladder diagram components. Everything that we had seen before has a reason why. So much emphasis on inputs and outputs is to simplify, much easier, make it much simpler on how to program. So here we need to understand a couple of concepts. We have as main components, or one of our main components, because if this didn't exist, there would be no ladder diagram. So our segment, our ladder, or our step, all of these names are correct. Depending on the brand, we can identify them with different names. So line is very common and we can use it. We know it as rung or rung, sorry, and AB, rung AB for Allen Bradley. Segment, I'm going to change color here. We know this from our Siemens brand. I ran a little bit of an abbreviation. And in English, segment, it's known as network. So that we can also start identifying and that we don't get confused when we're outside on the field, when we're working on the field. When they tell us, oh, well, segment or line, or we know what they're talking about. Step, this is a little bit more general. I've also heard certain Allen Bradley programmers, we can say, they sometimes can say ladder or step. Both of them are correct, but literally within their softwares, Allen Bradley knows them as rungs, and Siemens knows them as segments or networks. So then, what is a line? As its name says, step is from beginning to end this. All these times that we've seen them, that they have their contacts and everything else, and if it's denied, all of this completely, whatever it has, this is a line. There are certain brands which are also identified as line 0, line 1, line 2, etc. Here I made a mistake. Line 1, line 2. This can be line 1, line 2, or line 0, depending on how you have it identified. Okay, so perfect. Now what we have as elements or instructions for programming, all of this, all of these instructions, also these steps, all of this, generally everything that we see here on our left are permissions. And if they're permissions, they're inputs. For example, this denied contact is a permission. It can also be a push button. This is a regularly open contact. It is an input, and it can also be a push button or a pulse, a pulsar. This, even though it's an output, which is directed to this output, we're using an input. So then this is also on our input side. Now this is an indicator for us, which is indicating us if it's on, if my motor is on, or my fan, or whatever it is we're using. So this blinds us. So this is what tells us if finally we can power on that fan or that coil, and this is where we're going to allow the signal. Now, what I'm trying to get to is everything on our left side is input. Everything on our right side, which is generally devices to control or actions that we're going to run within our PLC. Now, these are inputs. And there's also instructions, for example, move, which is our math instructions, which are actions, and they're also on our right side. And we're going to look at this also further down. Now, also to simplify this, to simplify our concept even more, our adjective, if we take it, let's say, as a mission, our goal is to power on our coil, our motor, which is that this fan or whatever we have connected here, this should be powered on. Now, how do we power it on? On our left side, we have, and in a simulated manner, as a ladder diagram, we have an electric circuit. It's indicating that our device comes from our left side. And this in green, which means that the signal moves and moves and moves. And if it does power on, part of the coil, which is the positive side or the positive part, then that means that we're going to power on our device. Now, in theory, it says that we have negative voltage trying to simulate an electric circuit. That's why they did it. So then everything that's on this side, all of this, can always be on hold for positive signal. If we assign the positive signal and these starts complying, if this starts complying, this doesn't happen because this is still on, but this is a pulsar. If I press this, the signal is going to flow. And it's going to allow me to power on my coil, which allows me to feed on my right side, which means that it's always going to be sending a negative voltage. So all we need for this coil to power on uh, 0.0.1, I need to assign positive voltage. Now, how do I do this? I need to make my conditions or my inputs to comply or start activating. So far, so good? All right. So ladder diagram equivalency with electrical diagrams or electric symbols. That's why I left you the source here. I didn't do these symbols. I didn't create these symbols. These are general electric diagrams and drawings. So you can find them in ChatGPT or Google or a book. These are universal. Now, this page is based on this. Okay? Now, what are we going to identify and what we're going to ask? What I'm going to ask that you keep in mind, the electric symbol asks every device, in this case for input and output, to identify them, right? So manual contact, which is let's say a switch, normally open switch, it's actually a pulsar. Now, what does this do? How do we identify it with our diagram? We do need to learn this, for example, if we're electricians. And if we also move on the automation part, it's essential that we know their differences between each one because we also need to learn about their diagrams. But we're just moving on our programming part. To program what is asked of us, as a rule, is all these inputs, physical or whichever, we can substitute them with this symbol. All of these inputs, there's really no need to know if it's a floater or a mushroom switch or an emergency stop. Not really. Whichever we look at as an input, you will notice that we can change or modify with this symbol, which is a normally open contact. And if they ask us by saying a selector, for example, all we need to identify is if it's closed or open. And if it's closed, we just change it. Its equivalency would be this one. This one normally open. This one as well. Its equivalency would be this symbol. Okay? Perfect. So that's point number one. Point number two, ladder diagram equivalency, the same thing. The electrical part is indicating us to identify that device better, in a better manner. So this is a little bit more specific. It's asking me for that specific part. Here, for example, we have tri-phase electrical motor. Okay. Here we have a tri-phase motor with electrical startup, automatic startup, rotors, tri-phase motor with one direction. So they're asking us to be a little bit more specific because they have more symbols, especially for the ones who check the diagrams. We need to be very careful with this. Because remember that whatever the diagram says, in theory, is what exists physically. So we, for example, as designers, we shouldn't take this lightly. So when we read about this, we can compare this diagram with our electric symbols and we can see what they're indicating us. If we have a little bit more knowledge, then we know how to identify them, the symbols in general. So at a programming level, all of this is or equals this coil. Very simple, right? Now let's see if this is true. What is the equivalency in ladder diagram for this? Let's solve this, guys. Hit pause, use a piece of paper with your notepad, open up your PowerPoint, Mirage, or whatever you use, whatever you wish to use. What's the equivalency? Very simple. We have here regularly closed contact. This is the way it is, right? Regularly closed, open like this, again open here like this. How would this go? This is the way it goes. Now, this, we're being indicated about an additional contact, which is normally closed contact for overcharge, OL, or overload. This is a contact that if there were a failure, it boots everything. Here we have line 2. Here we have 2 lines for 220. Or if I don't see our voltage, I suppose that this is 220. And if not, it can be linear and neutral, just in case this doesn't work. So here we're closing our circuit. What's the equivalency? And now we can compare it. So what we're missing here is, as we can see, a regularly closed contact, which is the overload. And this we can add on this side. But ultimately, if you can see, this is normally closed, open, open, and our load or our motor. Now this contact we can omit, or we can add here. Okay? This is normally closed, and here we can add different input. Okay? This can be number 4. Yeah, this can be number 4. Okay, so again, just so that we don't get confused. So I, semicolon, 0.4. So we can assign this contact here and indicate that it's a specific contact for overload. Is there another way to do it? Yes, especially on our drive part, which is something a little bit more sophisticated. But this is the difference. What do you guys think? It's pretty simple, right? Let's go one step above. So ladder diagram programming. As I said, left to right. Step number 1, we have this PLC, and if it's fed, we can have as a regular state or status in standby, but we also have a status where we can activate as RA, the same way that we entered in our app as simulation mode. Our physical PLC also counts for this status. Okay, so it's already running, really. So when this happens, guys, most cases for our PLCs, we get them in green, or a color that we can tell that we're really indicating that the signal is on hold, which in this case is in green, okay? So here our signal, let's suppose that it is in off or standby for our PLC, which is where we can start modifying and adding different things. So once we're ready, we're prepared. Now, we're going to add our status or change our status for our PLC depending on the brand as rung. So it's ready to be tested. Now in this case, we're adding here a pulsar, a push button. This can be also a selector, but its position, its normal position, is open. So it's not allowing our flow, our energy flow. If we take this pulsar, this normally open pulsar, for example, this one on the top side, we have 2 borns. Okay? A born should be connected through one cable. And on the other side, it should be connected to another cable. So here we should have 2 cables. If we measure with our multimeter, our continuity is to know if we really have, as its name says, a continuity from end to end through this terminal and this terminal. We're going to notice that it is open. We can't hear a thing. That multimeter sound which is a continuity sound, which is if you hear that sound, then that means that there is continuity. This is normally open, guys. Now, what do we do if we read with our multimeter? We're not going to hear a thing because it's open. That's its regular position. So we're actually not getting any signal unless we press the button. But when we press it, internally, this contact is going to close and we already have a continuity. So as long as we have or we push this normally open contact, we read with our multimeter and we are going to get continuity and we are going to listen to that beeping sound because it's closing thanks to this button. Now, again, we're not pressing anything yet. So therefore, our output is not being activated. Step number three. So step 0, it's an off. 1, we already prepared our PLC. We're ready to look at the signal. And now we can press our green button, which is going to be closed. So therefore, we're going to allow finally an input from, we're going to power on my output. So we read from left to right. Remember, left to right, top to bottom. Now going back to our diagram, with our buddy, PLC boy. Finally, what we analyzed is all we need to do is connect our device and match this directive to our PLC. Now let's suppose that this is my input and I.0.0, which is this selector, which is like as if we had this one. Here we go. So open or closed, whatever you wish. Okay. This is your, as if your device is allowing you to do so. This is a 2-position selector. Okay, this is how it stays. So if this selector, if we had connected this selector to entry point 0, our PLC, the only thing it's going to do is it's going to receive a signal for that input. And all other devices are connected independently with all these inputs. All of these inputs are going to be connected to each one of these outputs. So it's, again, outputs with outputs, inputs with inputs, but they're independent. This can go to output 0, this one to number 1, this selector valve to output number 2, this one for number 3. So why am I indicating this? Why am I reinforcing this? Because our PLC, all it's going to do is it's going to indicate that for my 0 output, I have no voltage. Or for 0, I do have voltage. So what do you want to do with this? That's where we come in. And that's where we start creating our program. And we tell it, all right, so if your sensor or your switch, let's add, for example, your switch or your selector. Let's suppose we have this switch connected. Specifically for this input and the 2.0.0, I have this selector connected. If I don't get a signal, then don't power on. Don't turn off the lamp. Don't turn off the light bulb or whatever we have connected for my output, which is my pilot light, which is the one that's connected to my output or 2.0.0. With my switch, I can control this pilot light. If I didn't have anything programmed, whenever I'm energizing this or powering this, it's not going to indicate a thing because I wouldn't know what to do. But if I create my line and I add my condition or my conditional with my selector, that if I get voltage and I'm getting this signal, then now I'm going to get my lamp. Okay, so this is a video. Let's see how this works. Now, here, I'm allowing for my voltage flow for the signal, which means that here, I'm already converting to green. I'm already getting something. And if I'm getting something from here, I'm indicating it that it activates or that it powers on my public light, my light, my light bulb. So if I'm telling it, if you get some signal or voltage from this selector, then it's going to then power on the lamp. It's as easy as is. Everything that we're looking at here on the top part is a simulation. It's within our Animator PLC. This is a selector. We can change it through push button or selector. I changed it to selector so that we can really continue simulating through this device with our Animator PLC. So again, I power it on, I allow the flow for the signal, and power on the lamp. So again, it allows flow, and that's all that the ladder diagram does. Okay? Now, give me 1 second here. Okay. Perfect. So we're back now. So following the rules, left to right, top to bottom. Now let's go to programming. If I have a signal here that is interrupting or not allowing me to power on my output or activate my output, lamp, motor, whatever, it's not going to power it on. However, if I don't have a permission and I have to directly, as I move to my rung mode, and it's preparing my PLC ready to activate our outputs, then automatically it is going to power on all of this for exit point 1 to point 5 because there's no permission for this that is not allowing me to do so. So in theory, if we set the example with our drill for the PLC Animator, this program we're implementing through our exercise, let's say in real life, I'm indicating that only for our output or output 0 is not powering on. And here we go. This is the output. Output 0. Is it on? No, it's not. Why not? Because it's waiting for activation through button. So from output point 1, it's this one for this lamp, which is on. Let's see here. Point 2, where is it? This one is a lamp. I think it's an office, which is on. Point 3, it's also on. Oh, I remember now. Point 2, I actually can't remember if it's curtains or they're regularly down. I can't remember if it's point 2 or point 3, but one of these controls the curtains. And here we see that they're up. So they're also active. Point 2, point 3, point 1 as well. Point 4, this lamp at point 5, this other one. So all of this, except for point 0, which I'm adding the condition that we can control it with our switch. It's easy, right? So this is in bigger stakes, our ladder diagram. And now we're going to run our first drill, our famous hello world. So finally, we're going to solve our exercise, which is going to be on and the powering on and off of a fan. Our very famous hello world. our normally closed contact, and we're going to run our enclaving. So perfect, guys. Now, without further ado, thank you very much for your time, and I'll see you on our next lesson. Big hug, guys. Goodbye.